Hey everyone, welcome to your Grade 8 Physical Science Unit 1, Lesson 5 Explainer. I am so excited to be here with you today to unpack one of the most fundamental rules of the universe. We've got a really clear target for today's session. By the end of our time together, you are going to absolutely master using the equation F net equals ma. You'll learn to confidently distinguish net force from just a single applied force, and you'll be able to predict exactly how changing the force or the mass alters an object's acceleration.
Okay, let's dive into this roadmap that will guide our foundational physics learning today. We've got 1. Introduction to net force. 2. Newton's second law. 3. Modeling the calculation. 4. Changing force and mass. 5. Common errors and checks. And finally, 6. Recap and final challenge.
Starting right off with Section 1, Introduction to Net Force. What acts on an object?
So before we start crunching any numbers, we really have to ask ourselves, what is actually pushing or pulling on our object? This brings us to net force. In the real world, things rarely get just one single push. You might have gravity pulling down, friction scraping back, maybe you're pushing forward, all at the exact same time. The net force is the overall sum of all those forces combined. You absolutely have to combine every single individual push and pull to find the true final force that's actually going to change the object's motion. Moving on to Section 2, Newton's second law, the core mathematical law. And this brilliantly illustrates how we move from that basic idea of net force into the actual math that dictates motion. So here it is, literally one of the most famous equations in all of science. F net equals ma. Newton's second law simply tells us that the net force on an object, that total combined force we just talked about, is exactly equal to its mass multiplied by its acceleration. It's a beautifully simple equation, really, but it directly links an object's mass to exactly how much its speed and direction are going to change when you apply a net force. All right, Section 3, Modeling the Calculation. Step-by-step math. Let's get into the mechanics of this.
Let's actually bring this equation to life right now and model a calculation together. Seriously, grab your notebooks for this one. Step 1, we identify our variables. Say our net force, or F net, is 12 newtons, and notice that right pointing arrow. That gives us our direction. Our mass, m, is 3 kilograms. Step 2, we set up our equation by just plugging those numbers right in. So 12 equals 3 times a. Finally, step 3, we solve for our acceleration a by dividing both sides by 3. And boom, that gives us an acceleration of 4 meters per second squared. And since acceleration always follows the exact direction of the net force, it gets a right pointing arrow too. Also, pro tip here, always make sure you highlight those standard units, newtons for force, kilograms for mass, and meters per second squared for acceleration.
Section 4, Changing force and mass. Proportional changes. Okay, now that we've got a baseline calculation down, what actually happens if we start messing with those variables? It's kind of like a giant puzzle. If we push twice as hard, meaning we literally double the net force, well, our acceleration is going to double too. They are directly proportional. But what if we double the mass of the object while keeping our push exactly the same? In that case, our acceleration halves. It's inversely proportional. And I really want to explicitly remind you right here, mass itself is not a force. Actually, scratch that. It's more like a resistance. Mass is simply a measure of an object's resistance to acceleration. So a higher mass just means it's inherently harder to speed the object up or slow it down. Section 5. Common errors and checks. Frequent pitfalls to avoid. So the crucial point is knowing the most frequent pitfalls you're going to face when working with Newton's second law.
Let's quickly correct some of these common errors so you don't make them. Pitfall number 1, using just the total applied force instead of taking the time to calculate the true net force. Remember, you got to account for friction and opposing forces first. Pitfall number 2, reversing the equation mathematically, like dividing mass by force instead of force by mass. Don't do it. Always stick strictly to F net equals m times a. And the third big error, omitting your specific units. In physics, a number literally means nothing without its unit. So always include your newtons, your kilograms, and your meters per second squared.
All right, it's time for a quick pause check. I want you to literally pause the explainer right here and try this calculation on your own. If your F net is 20 newtons and your mass is 5 kilograms, what is your acceleration? Go ahead, hit pause, figure it out, and press play when you're ready to check your work. Welcome back. Okay, so if you calculated an acceleration of 4 meters per second squared, you nailed it. And here's the reasoning to back that up.
Our 20 newtons of net force is equal to our 5 kilograms of mass multiplied by 4 meters per second squared of acceleration. Easy, right? Let's try just one more. This is pause check number 2. Go ahead and pause the explainer again to predict a proportional change this time. Using that exact same 20 newton net force from our last problem, what happens to the acceleration if we double the mass to 10 kilograms?
Now, what's really interesting about this slide is how doubling the mass cut our resulting acceleration exactly in half. It dropped right down to 2 meters per second squared. Because our force remained a constant 20 newtons, spreading that same push over twice as much mass, 10 kilograms instead of 5, means the object can only accelerate at half the original rate. 20 newtons equals 10 kilograms times 2 meters per second squared.
Section 6. Recap and final challenge. Review and transfer. Let's move to and see how this builds into our final review and a really fun concluding cognitive challenge.
Let's lock this in with a strict 3-sentence recap of our learning targets today. Number 1, net force is the combined sum of all forces on an object, strictly distinguishing it from just one single push or pull. Number 2, Newton's second law states that F net equals ma. Number 3, increasing net force increases acceleration, while increasing mass decreases acceleration proportionally. Finally, I want to leave you with a real-world transfer question to chew on. Imagine a rocket fires its thrusters to provide a constant net force. What happens to its acceleration as it travels and constantly burns off its massive load of fuel mass? Think about how the mass is changing in real time, apply Newton's second law, and you'll uncover a genuinely fascinating truth about space travel. Thanks for hanging out and doing some math with me today, and keep exploring the incredible forces all around you.